All right, how's it going? So yeah, today I'm going to be talking about a secret network uh, research and development grant that I developed with my colleague Darwin Zero, representing the Starshell wallet. And what we set out to do was improve privacy aspects of secret network where there had previously been identified some slight privacy vulnerabilities with secret tokens. And also, probably more relevant to this event, is how can we scale secret network so that we could see like a 100x in user base, because there are some uh, scaling issues when it comes to trusted execution environments, um, provisioning that type of hardware in the cloud, and where can we, amend the stack of secret network to help it scale more. So if we could get started with the next slide. Let's skip this one. And okay, so yeah, so there's basically two major things. So the first one is something called storage access patterns. This is the privacy vulnerability I was talking about. And the second one is about how can we scale secret network. Next slide, please. Next. So let's go one step more. Yeah. So the storage access patterns. Let me just make sure I'm keeping track of time here. All right. So with storage access patterns, with confidential smart contracts, the which is how you secret tokens work, right? It's just a smart contract. It represents your share of a token. When you transfer, you're executing a contract. It's changing your balance and it's changing someone else's balance, and that's all it's doing. And those balances are stored in a database. Okay. The problem is that the whole database is encrypted. The problem is that each row is kind of like independent, and so this sits outside of the trusted execution environment. A malicious adversary can see that certain rows are being accessed at certain times whenever you execute a transfer. This row is being read from, this row is being written to. They can't see the contents of it because it's encrypted, but they can notice the same ones are being read from and written to if you're transferring to the same user. And this is what storage access patterns means. It's that you can infer that there is some correlation just by the patterns. So in this example, Alice is transferring to Carol. We're reading Alice's balance. We're writing Carol's, and yeah, this is the problem. So next slide, please. A better visualization of that same thing. We have our database over here. As you can see, these are the actual values, like Alice, Bob, Carol, but it's encrypted. So it's an encryption of that. Same thing for their balances, encrypted. But each one of these rows is independent. Okay, and then over here you have the trusted execution environment, the secure enclave, where you can't see what's going on inside of there. Next slide, please. And so your adversary can see requests being sent outside of the enclave to the database and back. One more slide, please. But it's all encrypted. So this is what an adversary sees in the data. They can't actually tell what the balances are or who the users are, but they can see the pattern, right? It's like it's always this row that's being updated. Okay, and then what's happening inside the smart contract is that this is where the actual data can be read. So we have Carol, we encrypt her key, then we can access it, we get the balance that comes right back, then we can decrypt that and we get her balance. Okay, next slide. Next slide. One more. Okay, so the simple way to get around this issue is, instead of accessing each row one at a time, we just bundle a bunch of things together. So we're hiding the pattern by putting it under one key. And the way that we access that key or that group is in the technical side of the details, but this is the overall gist. We sort of start batching things together in groups, and now we're able to hide those storage access patterns, because to an outside observer, all they see is that this one key is being read from and written to, but it's the same for all transfers now. It's not just dependent upon who you're transferring to or from. This is the basic concept. Next slide. Okay, so that was implemented with something called the delayed write buffer, and I'll just keep it simple today. So let's go to the next slide. Simple, but also kind of technical. So here's your traditional view of the keys being read from and written to. Then we add this extra data structure that is going to create a buffer between the contract interacting with that data and storing it to this database of balances. We batch everything together in one continuous row, but we hold up to, like a certain number of these queued or buffered transfer events. And by separating it out this way and then writing it later, we're doing something that's called smoothing in terms of computer science. We're creating storage access smoothing. Next slide. More technical stuff. Next slide. Next. Okay, and then, so to further complement this and increase the privacy even more, we invented another compound data structure, which I coined the bitwise trie of bucketed entries. It scales logarithmically in terms of complexity, if you're familiar with big O notation. And again, we're smoothing access patterns, but this time, instead of smoothing it for the event, we're smoothing it for all stored balances, for all roles. So this affects the sender, the owner, and the recipient, thus further enhancing privacy for all users. All right, next slide. Okay, so this is a little bit technical, but this is an overview of that data structure that I just mentioned, the bitwise trie of bucketed entries. So in the database for the stored balances, we no longer just have a single row per user with the key as their address and the value as their balance. Instead, we create this this complex tree of nodes that represent collections of balances or buckets of balances. So let's first imagine that we have one node in our tree. If you're familiar with any of this from computer science, if you're not, don't worry about it. This will just be a fun little exercise. So we have a bucket, which is basically a table of users with their balances and some extra metadata. And we need to insert a new row. We want to now add that Edgar just received 10 tokens. So we need to add this, okay? However, this bucket is full. So we need to split this tree into branches. So next slide, please. So the first thing we do is we split it. We get a new bucket, a new node. So we now have 3 nodes in our tree. And we need to add Edgar, but Edgar still needs to belong in this node. It needs to fit in this table because the hash of his address belongs in this part of the trie. It won't go here. So we need to split this node again. Next slide. Okay, so we split this node one more time. Now we have 1, 2, 3, 4, 5 nodes with 2 levels of height. And Edgar now finally belongs in a table where there is space. So we're going to move Edgar to this bucket. Next slide. And there we go. And so now we have just added a new entry in this data structure for a user who received tokens. And this compound data structure, each one of these tables is a different row in that database that I was showing before. And what this is doing is that it's smoothing the access patterns. So now, if we access any of these users' balances, an adversary won't know which one we're accessing. And they also won't be able to tell that this node previously belonged up here and is now moved down here. So we're smoothing patterns. All right. Okay, next slide. Just making sure I'm good on time. All right, and so finally, probably the most relevant part of this talk for today, helping the network scale. Next slide, please. Okay, so on secret network, there are certain challenges when it comes to adding a bunch more users, because when you are trying to query a secret contract, say for a balance, that request has to go into a secret node where it gets encrypted, fed into the trusted execution environment, ran inside of the enclave in a light client. The results get encrypted and sent back to you. So there's a lot of hardware required just for a simple query, whereas on an EVM, this stuff is cached outside of the nodes, can be queried very easily. So what we thought is, why can't we do that? Why can't we create a way of caching data outside of the trusted execution environment without compromising privacy, without revealing the balances of users, and ultimately really help the network scale? By leveraging non-SGX hardware. So in the cloud, we're renting all of these virtual private services that allow us to run trusted execution environments using Intel's SGX. But we want to use cheaper hardware that's more readily available to help us meet the demand of more users. Next slide, please. And that's what I just said. So next slide. How am I doing on time? How am I doing on time? Okay. This might be too technical. Basically, there is a process where we can listen to the chain for whenever certain things happen inside of secret contracts, even though it's all encrypted. And what this is revealing is basically how we're able to do that by using a feature in the Cosmos stack that writes, logs to the transaction logs, but it's all encrypted. This is sort of the basis for how it works, but it's not super important to understand. So next slide. Next slide. Okay, so yeah, so the consequences of that private notifications thing that I just skipped is that before the model, and currently actually, the way Secret Network works is that you have lots of clients and they're all querying these specialized hardware nodes that are running in the cloud on Intel SGX, which is what the trusted execution environment is. And what we're able to do now with this new feature called private notifications is we can offload some of that workload. We can move it away from those secret nodes because it has plenty of work to do. We're just going to take some of it away and create these multiplexers, which is just regular old, very simple, like you could run it on a Raspberry Pi if you wanted, computers that don't require SGX that can handle some of that work. That's the basic idea. Next slide, please. Okay, and now the exciting part, secret heaps. So next slide. So heaps stands for fully homomorphically encrypted and authenticated private storage. It is a layer 2 storage mechanism specifically for Secret Network that creates a private and unidirectional authenticated oblivious storage outside of the trusted execution environment. By oblivious, what that means is that we're avoiding storage access patterns, which I talked about in the first part. And so heaps is basically, you can think of it as like a cache outside of trusted execution environments. Next slide. And a very simple overview of how that works. Let's say that Alice transfers some tokens to Bob. What happens? Well, the first thing is, let's say she tells the contract, I want to transfer 120 tokens to Bob. The contract is going to emit very specific instructions to this cache, but it's all encrypted. It's going to say, okay, we're going to change Alice's balance. We're going to change Bob's balance. We're going to say Bob now has this. That all gets encrypted and emitted to the event log. Okay, so there's just this long string of digits and characters that no one understands, that no one can read. And that makes its way to the heaps node. The heaps node takes that instruction and homomorphically evaluates it on its database for that contract. So this is where the fully homomorphic encryption part comes in. It takes that instruction, applies it to every row, and it just updates everything at once and has no idea what changed. So it doesn't know whose balances were affected, but it actually does change the database. Finally, the result is that Bob can now get his balance without having to talk to the contract at all. He asks the heaps node, which again is running on very simple hardware. It says, what's the value, give me the whole database, or what's the value for this row? It gets that information. Bob is the only user who can decrypt the information about his balance, and now he's able to get that information. Okay, so next slide. So again, we're with fully homomorphic encryption, we're avoiding storage access patterns. Data integrity is preserved with other types of encryption, namely ChaCha20 and Poly 1305, so that no one except the intended recipient can actually decrypt the information about their key. So we're able to scale outside of the trusted execution environment without compromising privacy. And next slide. This is a more detailed view of how that actually works. So we have our database, we have the encrypted values of what we actually want to be able to tell the recipient. This isn't just for secret balances. This could be for anything. This works for any type of contract. Maybe you have a game and you want to store your inventory, or you want to update information like about direct messaging or social media. Anything can go in this private database. And then the fully homomorphically encrypted part prevents the heaps nodes from actually telling anything about whose balances were affected, because they apply an instruction, it affects the whole table, and we avoid any sort of storage access patterns. And then again, Bob is the only one who can decrypt that information. And this is how we're able to combine fully homomorphic encryption with trusted execution environments and gain a lot from the combination, not just relying solely on one type of encryption technology. And I think that's it. Let's go to the next one. Okay, next one. So finally, we're working right now on a new secret token that combines all of these things together. So the delayed write buffers for improving storage access patterns for secret tokens. We also have some extra privacy features like gas evaporation and private notifications, which is a really cool thing. And then the secret heaps as well, which I just talked about. So all of this is what we're doing to help enhance privacy for secret tokens and help secret network scale. And I think that's it. Next slide. Yep, that's it. Thank you, everyone. Sure, yes, sir.
You're going to deal with like on a client-to-client basis. You feel that relying on the storage of viewing keys from the client side is a little burdensome, especially if they lose the viewing keys?
Your question is about the burden of clients having to store viewing keys to get their balances. In this case, actually, we don't need viewing keys. Viewing keys is what you traditionally use, but for the heap stuff, the viewing key is actually derived from a shared secret between the client and the contract, so the user doesn't need to store it in any way. But normally, yeah, viewing key would just be something that you store in your wallet, the same way you would need to store like the address of the tokens that you have in your wallet. It's just another secret that's stored there.
Then you would need to have the viewing key.
Or you could create a new one to share with them. So you can create allowances, right? Or permissioned viewing keys where you can share, let's say to your accountant, you only want to share with him the history of like one of your tokens, or maybe only a certain date range. That is the sort of thing that you can do with permissioned viewing keys, which might be more applicable to those types of use cases. Yeah. Any other questions?
Yeah, well, is that IBM built software?
So SGX is a proprietary Intel technology, but AMD also has one. And I don't know if there's I think there's one or two other ones, but it is kind of, yeah, there's no like common global hardware T yet. I don't know. Oh, okay. Yeah, so AWS has one too, apparently.
I wanted to ask about FAT performance,
Mm-hmm.
because we all have heard that FAT is very slow
Yeah.
at the moment.
Yes.
And people are talking about special hardware that will speed it up. So how does it work in heaps? You know.
Yeah, yeah. Yeah. So some chains are using FHE for everything. And the trade-off to there is that it is actually very computationally expensive. The way that we're using it, fully homomorphic encryption isn't a silver bullet. It is a cryptographic tool. And the way that we're applying it is in a very performant way. We're simply using it to hide storage access patterns for these balances in the cache, in the heaps nodes. The trusted execution environment, it really excels in terms of performance. That's kind of how it beats out FHE and ZK, any ZK solutions. The way we're using FHE is complementary to that. So we're actually kind of getting the best of both worlds by combining these two approaches, which is really actually a pretty cool thing. I think that we're definitely the first production chain to do anything like this. I'm not sure if anyone else has even done anything like this, even in research. So it's a cool thing. We're excited to see how it performs. What's up?
More color on the utility of the token. And another question to follow up on that, so how will it play how will it play into the existing goal of the secret ecosystem? Because you guys already have the token, so how will that move dynamic?
Yeah, so the 250 is more of an interface. So we already have the 20, which a lot of tokens use. It defines a common way that wallets and dApps can get balances, execute transfers, like get query history. This is going to be an amendment to that spec. And so we're already working on a path to migrate all the existing tokens to this new standard. And then we're also hoping that new tokens that launch will simply launch as this new implementation that we've created. You mentioned color. One of the cooler things about this version 2 is private notifications. So right now, if I were to transfer some secret tokens to you, I would have to like send you a DM and be like, hey, I sent you the token, check your balance. But with private notifications, you actually get that notification right away. Your wallet is just there, like listening, kind of like how you get a push notification to your phone. Same concept. So your wallet actually notifies you, hey, I transferred secret tokens to you, and that's something completely new. Yes.
So, kind of like back to the HEAPS.
Mhm.
For the FHE, is it like fully homomorphic or it's just addition? Because if it's just addition, then I guess the performance is kind of.
It is fully homomorphic. The actual instructions is so like you couldn't do it with Algamal, for instance. The actual instructions are very simple. It's really more about the size of the vector, which is relatively small, and the circuit. And so the circuit is, I think, like 2 or 3 instructions. So it's very simple, and also one of the reasons it's quite performant. But there are some things we still don't know yet that we will learn once we develop and implement and start testing. But at the outset, it does not look like there's going to be any major like issues scaling to like tens of thousands of simultaneous like records in the database. So, or hundreds of thousands. Yeah. That is a great question. The vision right now is that this extra infrastructure, namely like the heaps nodes, the caches outside of the secrets nodes themselves, would be something that wallets and service providers would operate either as a public service or through community funding or however they normally get funding to operate their services, as well as dApps themselves. So a lot of dApps will operate their own infrastructure or provision nodes from node suppliers. This would be just like that. Maybe they want to create a heaps node for their contract and run that, and then their front end connects to it to get that information. And they would naturally be incentivized to do that because it's going to speed up the interaction with their app, right? It's going to greatly improve their user experience. So that naturally aligns with them, paying to provision that infrastructure in some way or another. As for wallets, it also improves user experience, so they would also naturally be incentivized. The incentivization really comes down to improving your own user client experience. Yeah. But the public services would just be for general use. If people do so, yeah.
Can those heaps nodes be deployed as part of the secret node? It can be just part of the main.
Yes, it technically could, but it would be taking away from the compute power of that node. You kind of want to reserve that for the enclave. Yeah.
The cost factor. They're not able, in order to reduce the cost they pay users.
The client does not have to run their own infrastructure. dApps and wallets, like the dApp operators, like Satoshi's Palace, for instance. They would be incentivized to run their own nodes or provision heaps nodes from providers because they would have a better user experience for their customers. No, but it could translate to cost savings for the provider because maybe they don't have to provision 10 nodes. Maybe now they can just provision like 5, and then the rest is made up for by these nodes that are doing offline computation. But we don't know that yet.
Amazing.